Here's a short remark. Here's a column where I'm feeding the pot. Turns out there's a number of problems like that in the problem set, and people have called my attention to them. And I thought I would make a remark on these. These are really the best kind of problem to get. First, you'll write FZ XDD plus XBD. If you know V and L, you can get D. So we have D. We have B, therefore. You look at this equation right here. It's one of these trial and error problems where you would like to know XD and XP. And the first thing to observe is that you guess an XD and go to calculate an XB. You will notice that as XD goes up, XB goes down. So every time you increase your guess on XD, XB will go down. You see it from that equation. Now, if I had a couple of plates here and I made a guess as XB, there's one other thing to observe, and that is this. I make a guess of XD. Here it is. I draw a line of slope R of R plus 1. There it is. I step down however many stages I've got, say 3 in a reboiler. For that XD, this is the XB. Now, if you move this XD upward, this XB moves up. So here you have an equation that tells you XD and XB vary inversely. Here you have a condition that says XD and XB vary together, which means that you ought to be able to converge any guess in most probably 2 trials. So that's a remark about these problems, so that you will think that every time you get a problem like that, you're pretty lucky. Now, we were talking the other day about, we got an azeotrope, and at some pressure, we got an echelon diagram that looks like this. And maybe it looks like this. The azeotrope is right there. Boss comes along and says, you've got to feed, you've got a rudder reflux ratio R. It tells you everything you need to know, and the problem is to go find, well actually, he might just give you let's take it this way. He might give you XD, XDD, or ZF. He says, go tell me the number of stages. Tell me the number of stages, tell me the feed stage location, and the feed stage location F. And so you run it at a pressure P. So you go out and find the equilibrium data, it looks like this. Feed is here. You make all your calculations, the bottom composition is here. And the top composition turns out to be here. And you say, there's no way I can do that, number one. Moreover, I don't care how much you change that reflux ratio, it remains that way. I can never do it. So you decide, well, we're gonna make this separation, so what shall we do? And here's what we plan to do. There's a number of things you could do, but here's the one we will do. You might find that if you change the pressure to a new pressure, so let's call this the pressure P1. If you change the pressure to a pressure P2, many times you can move that azeotrope, and maybe it moves to here. Azeotrope's now there. You say, I see what I should do. So let's sketch over here what we plan to do, and then it'll become clear. We need one more piece of information in order to do it. So we'll go get that piece of information. And it looks kind of like this. I'm going to build a column right here. Column 1 running at a pressure P1. Gonna build another column over here, column 2 running at a pressure P2. So here's this column. Now, in column 1 at P1, I got a diagram that looks something like this. So, in column 1, I am going to take a look at what I've got. Here's Z, here's the equilibrium curve. So what I'm going to try and do, this is the feed composition, so what I'm going to try and do in column 1 at a pressure P1 is that I'm going to try and make the XP, let's call it XP1, that the boss wants. But I'll try and make a overhead, say about maybe there, XD1, XD1, at some reflux ratio. And then what I'll do is, I'll go to column 2, here's column 2, running at a pressure P2. Things like that. Possibly it looks like this now. So I will take this, coming out the top of this column, and feed it over to this column. Well, I could have done myself a little more of a favor by increasing the P further. So I'll put a feed in this column. So this column will make a TOPS product, which I will then take and stick in here. So here comes D1, XD1. Here comes F and Z. Here comes B1, XB1. And I'll stick this XD1, XD1 over into column 2 running at pressure P2. I'll take a top product out. I'll take a bottom product out, B2, XB2. I'll see to it that this XB2 coming off the bottom of that column matches this. Design that column so we get that. So in this column, feed is that composition. The overhead is here. This would be XB2, XB2. And when I design this column, I'll be getting an XD2, XD2, XD2. this. So I'll be making a D2 and XD2. I don't want to throw that away, so I'll take that over here and stick it in this column here. So I'll take this XD2, stick it back in this column here, and I'll have my original feed here. I'll have my feed at XD2. I'll be making an overhead at XD1, bottoms at XB1. I'll stick that XD1 over here, make an overhead, well, make a bottoms at XB2, XB2, make a top at XB2, XD2, and I'll try and design a pair of columns that look something like that. The idea is that I will make the bosses specifications. That's the plan. Have two columns. Now, when we look at what we have to do, we see that we need to talk about 2 feeds per column. So that's what we'll talk about. We'll talk about doing a column with 2 feeds. So, in order to do that calculation, this is a standard calculation. There's one other thing that might be remarked about this. You know, every time we do a degrees of freedom calculation, we say, okay, the feeds are set, there's 2 degrees of freedom per stage. This, however, is 2 extra degrees of freedom. So when I go design these 2 columns, I've got some freedom here. I need to choose it sensibly, but yeah.
So is it common to find that the ratio of the K's of vaporization would switch like the relationship at different concentrations?
So a couple of years ago, I said to one of my buddies with computer skills, find me a system that acts like I want. So he goes on, screws around a while, and says, one of the butanols in the water will act just exactly like you want. You can move the azeotrope in butanol and water. You know, all these alcohols except for methanol have an azeotrope with water. So he says, here's what I find out. I find out you can move that azeotrope almost 10% by increasing the pressure from 1 atmosphere to 20 atmospheres. So that would be an example. Every example is different, of course, but so what are we doing? We're going to try and decide what to do with a 2 feed column. It's pretty straightforward. So let's talk about this. The boss says, okay, you've got a feed F1, a composition Z1, and an enthalpy HF1. You got a feed F2, and a composition Z2, and an enthalpy HF2. You're going to stick them into a column. Here's the column. I want you to run a reflux ratio, set the R, and of course you set this feed, you set this feed, set the reflux ratio, make all the usual approximations, of course, to see how the problem works. And the problem is to make a specification. So we set the reflux ratio, and we aim for an XD and an XDD over ZF. Now, what's a ZF, you say? Well, the ZF is F is F1 plus F2. ZF is Z1, F1 plus Z2, F2, HF, F is HF1, F1 plus HF2, F2. So you say, oh, I'm going to make my material balances around the column. This gives you D. You immediately get B. You immediately get XB. And so now you know what's coming out of the top and what's coming out of the bottom. gonna try and run the reflux ratio as advertised, and let's see what it might look like. So we do this. Here's our column. Well, let me put my diagram down. Here's a overhead product specification set. Here's a bottoms product. I have a Z1, I've got a Z2, and when I mix those, I get a Z, like so. And I got an equilibrium curve. Now, we say, we don't know how to do this calculation. So I'll tell you what, the boss will never check the pipes. We'll just take the stuff out of this storage tank, the stuff out of this storage tank, mix them, send them into the column. Seems like a good move. So you do, and that means you're feeding this, and you're running the reflux ratio assigned, and the equilibrium curve looks like so, and maybe the feed's saturated liquid when you get it all done. The other line's like this, and you say, can't do it at that reflux ratio. So you put your report on the boss's desk and say, boss, we can't do this at that reflux ratio, and then you go home. Luckily, what do you reckon happens? That's it. Boss, that's exactly right. So one of these University of Florida students who knows something, and you tell him I was working a problem, you know, and it won't go at the reflux ratio the boss wants. And the guy says, look, did you mix those feeds by any chance? You say, yeah. He says, don't you realize you've lost ground by doing it? You had them partially separated, you've mixed them, now you gotta stick them in a column and re-separate them. And at the reflux ratio assigned, you ain't got enough power to do that. So, you run home, have a sort of a restless night's sleep, race back into the office early the next morning, and repeat the calculation. So, that's what we're here to do, decide how to repeat the calculation. So we'll take our column and we'll number the sections in our column 1 and 3 and 2, and we'll see that making the usual approximations, 1 and 3 look pretty much like they did before. So I don't really want to erase that, but let's see if I can remember not to. And you say, okay, I'll call these flows, and one up here, L and P, and we'll stick in feed 2, call these flows L, double prime, V double prime, stick in feed 1, call these flows our usual notation, V prime, L prime. And you say, oh, look, we got the reflux ratio. So we can write the material balance up here in section 1 as we've always done. So in section 1, I know what to do. I got this XD point, I draw a line of slope R over R plus 1. This is the material balance in section 1 above the second feed. And I said, well, you know, I can get the material balance in section 3 very easily. All I got to do for the sake of making these balances is pretend like these things are mixed, make the balances as I've always done, and I can go to